This lab will walk you through experiment number 9, which is the alkyl halide solvolysis. So you're already watching the video. You are going to work the experiment and do the OWL assignment. So before we start the experiment, let's explain what is solvolysis mean. Solvolysis means that you're using a nucleophile which is the same as the solvent. And solvolysis is a simple SN1 reaction. And we know that with SN1 reaction, we have to work with a weak nucleophile, meaning a nucleophile that has no negative charge. So by using the term solvolysis, we can use an example, water, okay? So water is a nucleophile that is weak because it is a neutral, and at the same time, it can act as a solvent as well. So water is a nucleophile and a solvent at the same time, and this is what solvolysis means, using a weak nucleophile that acts as a solvent. So we know from the conditions of an SN1 reaction that the alkyl halide that we need to use has to be a tertiary alkyl halide. It can be a secondary alkyl halide, but it cannot be a primary alkyl halide or a methyl halide because these have no SN1 reaction. So if I give an example over here of let's say, if I give an example over here of 2-bromo, let's say if the bromine is up there, this is a chiral center, this is a 2-bromo butane, and I am reacting this with water. So that is an example of a solvolysis reaction because water is a weak nucleophile that acts as a solvent at the same time. So this is an SN1, and at the same time, this is a secondary alkyl halide, so the reaction can work. The reaction happens in 2 steps. The first step, the bromine is going to leave. So when the bromine leaves, you are going to create a carbocation. And the carbocation has to stand on its own, so it has to be stable. And this is why we say that you cannot start with a primary alkyl halide or a methyl halide, because both of those will generate a carbocation that is not stable. Secondary alkyl halide will generate a secondary carbocation, and a tertiary alkyl halide will generate a tertiary carbocation, and both are going to be stable. Remember, in this reaction, you can also do rearrangement if you can. So you can go from a secondary to a tertiary, but here we cannot, because if you move the plus charge here, it's secondary. If you move it here, it's a primary. So it's still going to be secondary, so this is why you cannot do any rearrangement, so we can proceed in this step. So that is going to be step number 1. So step number 1, we're going to make the carbocation, and we already made it. And now step number 2, the nucleophile is going to attack. The nucleophile cannot attack in step number 1, and the reason why, because the nucleophile is weak. So this is why you need to create a stable intermediate. So your secondary carbocation is a stable intermediate. And that intermediate, you're going to use it as a reactant in the second step in order to create the product. Do not forget that this is a planar carbocation, and that planar carbocation, I know that I do have a hydrogen in here. This one is not chiral, right? So your reactant in the second step is optically inactive. So this one is optically inactive. So this means that any product that is going to be generated from this step should be optically inactive, okay? So now in the second step, we are going to use water, and the reaction goes by 2 ways. Water, because this is a planar molecule, the carbocation is planar, it's an sp2 hybridization. Water can attack either from the top, or water is going to attack from the bottom. And you have to consider both of the cases, you guys. Okay? The reason why I'm showing stereochemistry, because at the beginning I am given a bromine to be up. And I am starting at the beginning with a chiral center. So this is a hydrogen. Remember, every tetrahedral carbon is 2 bonds in plane, 1 bond behind, and the other one is in front. So I'm starting with a chiral center. If you're starting with a chiral center, then you should show the stereochemistry of your reaction. So the product is going to proceed by inversion and retention and configuration. So water in this case can attack either from the top and will generate an OH that is actually on the top in there with 8 plus a charge. This is water, okay? And later on, I'm just going to use water as a solvent. So you see, this is why it's called a solvolysis reaction, because you're using your nucleophile to attack the plus a charge, and then you're using it as a solvent to act as a base to take the acidic hydrogen. So this one now is going to act as a solvent. And we know that the solvent here in this case is basic, so it's going to come and take the acidic hydrogen. You're going to do an acid-base reaction, and you are going to create your product. In this case, this is going to be our first product where the OH is going to be up. Okay? And of course, you do have your hydrogen, which is at the back. So that is going to be product number 1. And product number 1 will proceed by retention and configuration. So see, the bromine is up, the OH is up. So that one is going to be the retention in configuration. And now water is going to come and attack from the back. And when it attacks from the back, you are going to make, you're going to form your water at the back. And then water is going to act as a solvent in order to come and do an acid-base reaction again. And you're going to form the inversion in configuration. So see, now your OH is going to be at the back. So that is going to be the inversion in configuration. This is product number 2. I would say that both product 1 and product 2, these are the products of this reaction. So always SN1 leads to 2 products. One is retention, the other one is inversion in configuration if I am starting with a chiral center. And those 2 products are going to be a racemic mixture. See, at the beginning we said that because the reactant in this step that leads to the product is optically inactive, then the product has to be optically inactive. So this is why both of these are going to lead to a racemic mixture, meaning that 50% is going to be R, the other one is going to be 50% S. So one rotates the plane of polarized light to the right, the other one to the left in there. So it's as if like the plane of polarized light is not rotated. Okay. This is how you do a mechanism for an SN1 reaction. Now, guys, remember that with SN1 reaction, you also have rearrangement. So let's say, for example, if I'm starting with something like this with a chlorine, and I am reacting this with water. This is again also a Solvolysis reaction. It's an SN1. Always double check and make sure that you are starting with either a secondary or a tertiary alkyl halide. This guy is a secondary because you look at the carbon that is connected to the chlorine and you see that it is connected to 2 carbons, 1 and 2. So it's a secondary alkyl halide. So we said like the first step, the chlorine is going to leave. Let's say if the chlorine here is on top, hydrogen is at the back. So chlorine is going to leave, and when the chlorine leaves, you are going to make your carbocation. In this case, this is a secondary carbocation. Now you pause and you ask yourself, can I make this carbocation more stable? Well, yes, I can make it more stable if I take and move this hydrogen over here together with its bonds. So that is going to be a hydrogen shift towards the positive charge. So it's going to be a hydrogen shift over here towards the plus a charge. Here you go. So I can do a hydrogen shift. Never do a CH3 shift if you have a hydrogen shift. So you look at your adjacent carbon and say, okay, I can move this hydrogen here and create my plus a charge there, which is going to be tertiary, more stable than the secondary. So I'm going to make my carbocation in this case, which is a tertiary carbocation. Notice that your carbocation is not a potential chiral center because the two groups over here are going to be the same. So I'm not going to go ahead and consider the stereochemistry for the reaction because it is not a potential chiral center. So that was step number one. And step number two, because it's not a potential chiral center, do not bother with the mechanism of the reaction and having water attacking from the front and from the back. Again, because if you can see over here, these two groups are the same. So you don't have three different groups and you add a fourth one to be a chiral center. There is no possibility of chiral center in the product. So if this is the case, I'm just going to move by just having one product in there. Water is going to attack since there is no chiral center, and then you're going to end up having the same idea. Water is going to form a positive charge on the oxygen. Remember, always with organic products, your product has to be neutral. So we're going to use the water again. This is why it's a solvolysis reaction. The nucleophile acts as a solvent. And our product in this case is going to be an OH, which is a tertiary alcohol. Okay, so again, whenever you are working with an SN1 reaction is a two-step reaction. The first step, you make a carbocation, but every time you make a carbocation, ask yourself, can I make it more stable? If yes, you can move a hydrogen. If there's no hydrogen, there should be a CH3 to move. If no, then you can go ahead and continue with the carbocation that you have. Once you make your carbocation, allow the nucleophile to attack. If there's no chiral center, do not show stereochemistry in the product. But if there's a chiral center, then the attack or a potential chiral center, as in the case up there, then the nucleophile is going to come and attack from the top and from the bottom, and you're going to form two products that are racemic mixture. So with this said, this is going to be the mechanism of the solvolysis reaction. You can use this and write down the mechanism of the compound that you are going to synthesize in lab number one. So to access lab number one, you're going to go to the experiment, and then you are going to go into the experiment assignment, and this is your experiment. So this is the purpose for the experiment. So what we want is to make the 2-methyl-2-propanol. So start by drawing your 2-methyl-2-propanol. So let's draw the 2-methyl-2-propanol over there. This is going to be our product. So we're going to draw the 2-methyl. This is going to be the 2-methyl-2-propanol. So here it is. This is going to be the OH. This is the propyl group. This is going to be carbon number 1. That's going to be carbon number 2. So it's going to be 2-methyl, 2-propanol. You got to know your reaction in there. So this is going to be our alcohol, right? And they're asking us to make it. So to make it, I know since this one is a tertiary alcohol, you got to know what type of alcohol you have. So it's a tertiary alcohol. Why it's a tertiary alcohol? Because you look at the carbon that is connected to the OH, and that carbon that is connected to the OH is connected to 1, 2, 3 carbons. This is why it's a tertiary alcohol, right? So if it is a tertiary alcohol in this case, because I lack the number of carbons, I only have 3. So definitely it needs to come from a tertiary alkyl halide. So the halogen can be either a chlorine or it can be a bromine. It really doesn't matter. So I have to start with a tertiary alkyl halide, which is going to be, it's going to be 2-chloro or 2-bromo. 2-chloro or 2-bromo, it doesn't matter the halogen again. So 2-chloro, 2-methyl, propane. This is going to be my reactant. And then if I react this with water, then I'm going to go ahead and end up getting my OH in this case. Notice that the alcohol that you are starting with is not a chiral center. So this one over here is not a chiral center. So when you draw, guys, the mechanism of the reaction, you don't have to show the chiral center. It's going to be only one product in there. Okay, so I know now that I need to start from 2 chloro, 2 methyl propane, and I need to use water as a solvent. So I'm going to start opening my experiment. So this is going to be my experiment. I always open it in a new window and allow both the procedure and the experiment bench to be on the same page. I give more space to the experiment bench so that I can see everything. Now the experiment is going to open on a page where you're going to see the reaction. We're going with alkyl halide solvolysis, and you have all of these solvents to choose from and all of these starting material to choose from. So we agreed to make the 2-methyl 2-propanol. We need to start with the 2-chloro 2-methyl propane. Over here, you do have your flask. This is your reaction flask. And by simply clicking on any one of these, it's just going to immediately go into the flask. So we need this. We need the 2-chloro 2-methyl propane. So we have that. We can hover over the contents of the flask and we can see it in the window. So you see in the window over here, the tertiary butyl chloride. This is the common name for 2-chloro 2-methyl propane. This is what's inside. And then what we need from here is actually the water, because it's a solvolysis reaction, right? So if we hover over here over our flask, we're going to see we have both the tertiary butyl chloride and the water in there. Just make sure that you have the contents that you need in your flask before moving it into your working station. So now I'm going to move my flask into the working station. I'm prepping now for my synthesis because this is a synthesis reaction. And in an actual lab, this is what you need to do, actually. You fill your flask with the materials that you need for the reaction, and then you bring your flask into the working station. Now, in the working station, what do we have? We have a hot plate, and then we do have over here a heater. We use the heater in order to distribute the heat evenly and around the round bottom flask. Now, it's obvious that we would need to heat our reaction in this case, but we don't need to heat it too much. It's a fast reaction, and we are not doing any elimination in this case. So this is why we don't need to heat it much, and the reaction is going to be really fast. We are going to use in every single synthesis problem, we have to use a condenser. So what is a condenser? A condenser is a glassware. It's a piece of a glassware that cools down our mixture while it is heated by having water flowing in and out. And this again cools down the reaction mixture. And then for every synthesis in Beyond Labs, it does create a lot of pressure here. So this is why we need to ease the pressure by simply adding nitrogen gas. If you forget to add the nitrogen gas during the process of your reaction, the flask will explode. So you have to start all over again. So this is going to be our setup. So that is going to be our setup. And normally we use this in every single synthesis. You need your flask, you need your condenser, and you need your nitrogen gas. We don't need any of these chemicals in here because in the solvolysis reaction, this is everything that we need and it's going to be in our flask. Whatever materials you have in here, these are after you do the synthesis. So when you do extraction, we are going to use those. So we're just going to keep those aside. Before we start our reaction, every single time you have to take a TLC. The TLC is going to be at the beginning of the reaction and at the end of the reaction. So if you scroll over here while you're making the experiment, you have to fill up whatever you need to fill up. So we're going to list the starting materials. So what are the starting materials in here? The starting material are our reactant and our solvent. So you can write them like this by name. Now, if you choose to write them by the molecular formula, please use an underscore between the letter and the number. So I would write it as an H and then an underscore and then a 2 and then O. Okay? Or you can write it as water if you want, which is I prefer to write it as water. So here you go. So our reactants, you have to list your reactants and you have to list your product as well. Our product is whatever is asked from us to synthesize, which is actually the 2-methyl 2-propanol. So you are going to list it over here as well. And then it says like, how long did it take to finish the reaction? Guys, before you answer this, we have to take a TLC. We have to take a TLC for the starting material. So don't answer this, don't start the reaction before doing a TLC. So this is the TLC plate. So we're going to go ahead and bring the TLC plate all the way to our flask. So once we bring it to our flask, here's what you have. This is always there. This one is a reference. Okay, so this one what's supposed to be our reference in there, and whatever is on the right is whatever is in the flask. So this is the reactant in the flask, which is the 2-chloro-2-methylpropane. Right is whatever is in the flask, and in the flask we have the 2-chloro-2-methylpropane. So you are asked to calculate the RF of the starting material. There is no scale on this TLC plate, so you would need to bring your ruler and put it on the screen. You guys bring your ruler and put it on the screen in order to measure the distance. And by now you should know how to measure the RF of the spot. So from the center of the spot, you are going to take your measurement. You're going to start your measurement from the spotting line to the center of the spot. And then you're going to do another measurement from the spotting line into the solvent front. And then you're going to divide the small distance over the large distance. Your value for the RF is always less than 1. It cannot be more than 1. It doesn't matter what units you use. You can use millimeters, you can use centimeters. It's really up to you because the units are going to cancel out. But whatever value you get, it needs to be less than 1. So this is going to be our reactant in this case. We're going to save the TLC plate, and I want you to save it because I need to see your lab. At the beginning, I asked you to join the class with a code, so you should have done this by now, okay? So we're going to do save lab, so we saved it, and we're going to do save the lab in there. If you go to your lab book, you should see your TLC plate at the beginning. We're going to go back to the live data over here. This is going to be your TLC plate, and this is going to be whatever is in the flask, the alkyl halide and the water. Whenever you're doing the experiment, you should always open up to the live data just to see the contents of your flask, because as the reaction is proceeding, you're going to form your product in there. This is how you know when to stop. So we're going to take your TLC plate, and now we're going to answer this question by starting the reaction. So to start the reaction, by the way, before we start the reaction, we have a clock in here, and the clock moves by an hour and by minutes in there. So this is every 10 minutes in there, and this is every 1 minute. So we can simply speed up the reaction by 1 minute, 10 minutes, and an hour. Never do the hour. Never do the hour, except if the experiment is very, very long, that we go with hours. But we're going to start first with the minutes, okay? I'm going to start with the minutes. We can do either a 1 minute or we can do a 10 minute in there. So we're going to start our reaction by hitting the start reaction button. And you're going to see that your contents of your reaction are going to stare, right? So right now there is nothing in there. It seems like I am not heating the reaction, because heating the reaction again will make elimination. So you're going to end up getting your alkene rather than getting your alcohol, your substitution. So this is why here it seems like I am not heating anything. Okay. I'm going to start by processing the reaction, increasing the time by 1 minute, and see, I formed my product in there, which is the 2-methyl-2-propanol. So always take a look at whatever you need to form in there and make sure that you formed it. Now, we want to push the reaction to completion, right? So we don't have any organic compound other than this guy over here. So I believe that the reaction has stopped in there. So let's go ahead and do another 10 minutes. So we did a 20 minutes. So after 20 minutes, just on the safe side, we did form our reaction. So after 10 minutes or 20 minutes, it doesn't matter. So how long did it take for the reaction to finish? Probably 10, 20 minutes in there. I have my product, and I have this as a byproduct. This one is an inorganic byproduct that I can get rid of by simply extraction after I'm done from the experiment. So now the experiment is done. Okay, so I'm done making my product in this case. Now what I need to do is purify it, and the purification comes by either extraction or crystallization. We do crystallization if our product is a solid, but here our product is a liquid. So we're going to do extraction. This is how we're going to purify it. So see that separatory funnel, this is the extraction in there. So we're just going to go ahead and take the separatory funnel and let it touch the flask. So by doing this, our contents in the flask will transfer into the separatory funnel. So now in the separatory funnel, what we have, look at the live data, what we have are these two over here. Our purpose is to isolate the hydrochloric acid, take it out. So hydrochloric acid is what? Hydrochloric acid is an acid, right? And to get rid of an acid, we have to react it with a base. We have two options, either use water or use NaOH. I would prefer to use NaOH in there so that I would do an acid-base reaction with the hydrochloric acid and neutralize the hydrochloric acid. When you do extraction, you know that you have two phases. You have aqueous and organic phase. The system will immediately add diethyl ether over here. So the moment you take your NaOH and you put it in there, you're going to see that the organic layer has diethyl ether there. So you're going to ask, from where did the diethyl ether come from? This one is an organic solvent that it has to be there. You have to add it every time you are making extraction so that you create the two layers, the aqueous and the organic. So now when we added the NaOH now is present in the aqueous layer and it took with it the HCl. So if I bring my cursor to the aqueous layer, you see that you have hydrochloric acid in it and water. This is neutralization, okay? And then the top layer is the one that I need, that has the 2-methyl-2-propanol and the diethyl ether. The diethyl ether will evaporate. So this is it. I got my product. So now we're going to go ahead and take the organic layer. So I'm just going to transfer that organic layer immediately, like a round bottom flask will appear on the screen. Just the organic, and I'm going to place it over here. So this is it. This is my product, and just to make sure over here, I'm just gonna look and bring my cursor to my flask and look at the live data, and I see only the 2-methyl-2-propanol. Every time you synthesize a product, at the end of the reaction, after your extraction or after your purification step, look at the live data and look at the flask contents, and you should see just one product, the one that you are asked to synthesize. You should not see multiple. If you see multiple, then you did something wrong. Okay? I don't need this, so you can simply dispose it. Over here, we can clear it. And now it's time to take the second TLC because it asked me to find the TLC value for the starting material and then what is the RF value of the product. Now I need to take TLC for the product. Now you're going to see that the TLC for the product is different than that of the reactants. Look, at the reactants, I'm starting with the reactants over here. Now my products are more polar because it is an alcohol. So it's more polar. I'm expecting to have a lower RF value. So you're going to calculate the RF value of the product again by measuring the distance from the spotting line to the center of the spot. And you divide that from the spotting line, or you divide that by the distance from the spotting line to the solvent front. And you should get a value for the RF, and this RF value has to be lower than that of your starting material in there. Okay, we're going to save the TLC again so that when I go into your lab book, I can see all of this data. To draw the mechanism of the reaction, just go ahead and open a file, draw the mechanism, or you can draw it on a piece of paper, take a picture, and then upload. You guys, if you cannot upload the file, but you should. But if there's a reason why you cannot upload the file on Beyond Labs, then what I did is I created I did create on eCampus a folder for you. So if you go to your course, let's have an example over here. So if you go to your course content, I mean, you should see here upload for experiments 9, 10, 11, and 12 mechanisms. you can upload it here for experiment number 9. You're going to do the same thing for 10, 11, and 12, but this is your last resort, you guys, because you should be able to upload all of these files on Beyond Labs. Okay, you should be able to do this. So always save your lab just to make sure that we have all our lab data saved. After you go ahead and submit your mechanism. And by the way, this one is very important to submit, and it's out of 20 points. So please do not skip this. So please do not skip this. And I want everybody to submit their mechanism for the experiment, and then we have a spectroscopy data to answer data over here. So we do have the IR spectra, and this is the proton NMR spectra. So we can take that IR, so this is the IR disk in there, and we can bring it to the flask. And then immediately we're going to see an FTIR spectra popping. So here you go. We're going to read the FTIR spectra from the left to the right. And we already know, let me open this, we already know our product in this case. So what is our product? Our product is an alcohol. Open another page in there. So our product is an alcohol, and we would need to look at the alcohol functional groups. So that is going to be our alcohol. So this is going to be the FTIR. Always look at your product and see what type of functional group do I have. So the functional group over here is the alcohol, right? So I am looking for the FTIR. I am looking for my first group, which is the OH vibration. And the OH vibration is a broad peak. This is the OH vibration in there. And that should show between 3,600 and 3,200. Actually, over here, it's showing between 3,200 and 3,600. Yeah, or you can say it's around 3,400 if you don't want the range. It is around 3,400 centimeter to the -1. So this is going to be peak number 1. Every OH has 2 peaks. It does have the vibrations at a higher wave number, and this is the stretching vibration. And it does have a bending vibration as well, and that is around probably around 1390. So again, the OH is gonna show at 1390 centimeter to the -1. This is around 1400 or 1390, and this is going to be the bending vibrations. So this is going to be the bending, this is going to be the stretching. The stretching always appears at a higher wave number than the bending. So these are the 2 peaks that we care about for the alcohol in there. And then we have a third peak, which is for the alcohol, which is the CO stretch. This is the sp3 CO stretch in there. So that is going to be the CO stretch. And that CO stretch needs to appear because it is the CO. So CO means 1200. So 1200 centimeter to the -1. So these are the 3 peaks that identify that I have an alcohol functional group in the FTIR. The second part is the proton NMR. So in order to get the proton NMR, we're just gonna take the tube of the proton NMR. This is where you put your sample, and we're just gonna bring it towards the flask there. And the proton NMR graph is gonna pop up. And you can see over here, I only have 2 signals. You read the proton NMR from left to right, just 2 signals. This one is going to be just the reference. It's a 0. We don't care about it. It's not part of our structure. So our structure here has two signals. One, and both are singlets, if you can see. So let's go ahead and look at our structure. So our structure there, we said that every different hydrogen has a signal. So let's write down the hydrogens here. So it's a CH3. All of these CH3s are the same. So I'm expecting those to be proton A, proton A, proton A. And because the first signal that we always see in the proton NMR is a CH3, so this is going to be peak number 2. So peak 2 is going to correspond to all of these CH3s that you see there. So this is going to be peak number 2. And we can read the chemical shift for peak number 2 to be at 1.26 parts per million. And then for the multiplicity of that, meaning how many peaks it's split to, it's a singlet. It's a one peak. Why? Because every single one of these hydrogens is not connected to a hydrogen. So it's n plus 1, so it's 0 plus 1, so it's a singlet. It's a one peak. So that is going to be a singlet. This is going to be the multiplicity for peak number 2. Peak number 1 is going to be our OH, which is the second signal in this structure. The OH is going to is actually going to spin. This hydrogen is going to spin, and we said that OHs and NHs, they do not split. They always appear as a singlet. Even though if there are hydrogens next to them. Now this one doesn't have any hydrogens over here, but it doesn't matter. Even if it has a hydrogen, always the hydrogens from the OHs, the NHs, they appear as one peak as a singlet. So for the OH is going to simply show at 3.6 parts per million. And the multiplicity for that is going to be a singlet as well in there. And that is going to correspond to what? So they're going to ask you in the proton NMR, is going to correspond to how many hydrogens? Well, it is one hydrogen. So it's going to correspond to one hydrogen here. Peak number 2 is going to correspond to how many hydrogens? Just add those up, and it's going to be 9 hydrogens. Guys, you can do the area, you can do the integration as we did earlier in the first proton NMR lab. And even if you do the integration, you're going to see that peak number 2 is going to correspond to 9 hydrogens, and peak number 1 is going to correspond to 1 hydrogens. Please submit your labs on time. If you have any questions, please let me know.